A reversible gold and blue reaction by Sophia Newton. These are the materials we're going to need to perform this experiment. From left to right, we have pipettes, a 100 milliliter graduated cylinder, 3% hydrogen peroxide, copper sulfate pentahydrate, and sodium potassium tartrate, along with some distilled water. The copper sulfate and sodium potassium tartrate solutions have already been made. Now let's do the experiment. Before this, I had already placed 25 milliliters of 1 molar potassium sodium tartrate at 17 milliliters of 3% hydrogen peroxide and a magnetic stirrer into a beaker. Then I placed the beaker on the hot plate and heated the solution to 50 degrees Celsius and turned off the hot plate. Once the solution reaches 50 degrees Celsius, 0.42 milliliters of copper sulfate pentahydrate are added to the solution using a pipette. Observe the initial slight change to a blue color and then the formation of an orange cloudy substance in the solution after the copper has been added. After the initial reaction between the three chemicals, the mixture reaches equilibrium and will stay in its orange precipitated state. However, if we add another portion of hydrogen peroxide, an interesting phenomenon can be observed in the solution. Now that we've seen the experiment firsthand, we can delve a little deeper into the mechanics of it. What you see here is the balanced chemical equation of the first reaction that happens in the experiment. When the copper sulfate pentahydrate is added to the existing hydrogen peroxide and potassium sodium tartrate solution, the copper and sulfate ions dissociate and the copper 2 ions bond with the tartrate ions to form copper tartrate, which is a complex ion. In the next reaction, the same complex ion reacts with hydrogen peroxide. The complex ion catalyzes the decomposition of hydrogen peroxide into two different gases, CO2 and O2, which accounts for the bubbling that can be seen in the solution. It also produces copper oxide, which is a solid and accounts for the orange cloudy precipitate that is formed. The oxygen in hydrogen peroxide has the oxidation state of -1, allowing it to both reduce and oxidize. The hydrogen peroxide reduces copper 2 to copper 1 and is reduced to H2O, producing copper oxide, the orange cloudy precipitate you can see in the experiment. On the top of the whiteboard up here you can see a diagram of the copper tartrate complex ion, with the copper ion in the middle and the tartrate ion surrounding. After a second portion of hydrogen peroxide is added, it acts as an oxidizing agent, oxidizing the copper 1 ions in copper oxide into copper 2 ions, which reform the complex ion with remaining tartrate ions and turn the solution blue again. In the competing reaction between the complex ion and hydrogen peroxide, the excess or leftover hydrogen peroxide reduces the copper 2 ions that were just oxidized and turns them right back into copper oxide, effectively returning the orange precipitate. This phenomenon is perfectly described and accounted for by Le Chatelier's principle, which states that if an outside stress occurs and disturbs equilibrium, equilibrium will shift to counteract the change. In this case, it is slightly more complex because the principle is acting on two conflicting chemical equations. Firstly, when a second portion of hydrogen peroxide is added to the solution, it adds an outside stress to the left side of the reaction, or the reactant side, which causes the reaction quotient to decrease. To keep a constant, equilibrium must shift towards products, causing the oxidizing of copper oxide into copper 2 ions. These copper 2 ions combine with the leftover tartrate ions floating around in solution to reform copper 2 tartrate complex ion, bringing us back to the above equation. Excess hydrogen peroxide from the second portion puts an outside stress on the left side of the equation as well, again causing the reaction quotient to decrease. This means the equilibrium will again shift toward products to compensate for the addition of the hydrogen peroxide, which will again produce the orange precipitate of copper oxide. Though I did not use balanced chemical equations for a few of the equations during my explanation for clarity purposes, here are the balanced chemical equations for your reference. Thank you so much for listening, and I hope you've had fun watching this very interesting experiment and learning a bit about it.